So our next talk is by John Rebula from the Max Planck Institute.
Maybe. Yeah, okay. Okay, so the overall goal of this work is to get at preferences during locomotion. So for example, when you walk on a treadmill for a long time, you're going to get bored and you might find yourself prioritizing energy economy quite strongly. So you're going to do the minimum amount of work it's going to take to not fall off the treadmill. However, if you start messing with someone's sensing, or we start perturbing you, you might start prioritizing stability more and energetic efficiency less. Or you might do more work to avoid sharp, painful impacts with the ground. So it's not always easy to pin down the relative importance of these priorities, but it does seem like there are trade-offs going on. So what we want to do is use some simple dynamic walking models to get a feel for how people will behave in different circumstances and tease apart the effects of considering different cost components. So this is quite difficult. So we are going to first develop methods here to predict the behavior of complex walking models using simpler walking models because we have ground truth for the cost functions in this case. Okay, so the way that we model an experimental subject or any walking thing in this work is as an optimizer. So when you're faced with a task such as taking a step, the idea is that you find a step represented here as x that minimizes the cost. So the optimal control is the process of, given the cost to minimize, find a trajectory of states and inputs to minimize it subject to the limitations of the walkers and the task constraints. So we call the optimum x star. And what we do here is the opposite of that. So we are interested where, in a case where we have x star and a set of assumptions about the constraints of the model and task, and our goal is to infer the cost function. So to simplify the problem a bit, we're going to assume that the cost function has this form where you have a weight vector w times a feature vector, where the feature vector might include things like joint power squared and some stability metric squared integrated over the trajectory, just some things you might want to minimize while you're walking. This changes the picture a little bit because now if we are given knowledge of the features that were considered by the optimizer, the goal is to estimate w, the relative weighting between them. So as an example, if you consider the compass walker, the features that we're going to consider are the sum of the applied hip torque squared over the step, plus an error in the step length away from a nominal desired value. Okay, I lost it again. Okay, and then we're also going to gather all the constraints associated with the model and the task. So things like F equals MA, integration constraints, limit cycle constraints, and we're explicitly here specifying contact conditions, and so on and so forth. We get all the constraints, and then we also choose some weight vector W. Then, given the weights, features, and constraints, we can form a nonlinear optimization problem, which we can just pass to an off-the-shelf optimizer and solve for the step that best optimizes this cost function. So for some set of weights, this is what it looks like. And the goal here is to figure out those weights that we used. So just to sketch out the procedure pretty briefly, I did this, someone did this for me last year, but it's always fluid. So the first thing we do is we're bootstrapping this procedure by finding a bunch of suboptimal trajectories. So to do this, we add some noise to the optimal trajectory. So we have a whole set of trajectories that are suboptimal, but don't satisfy the constraints of the model and the task. So what we next do is project these noisy suboptimal steps, non-steps, into the constraint space, and we get a bunch of feasible suboptimal trajectories, x minus. Then we perform another optimization. So this time it's over a set of candidate weights, WC, constrained such that the weight vector is consistent with the optimal trajectory, x star, having lower cost than all of the suboptimal trajectories, everything in x minus. So this gives us a set of candidate weights that we can now use to produce a new stepping trajectory using the same task constraints as in the original problem definition. If the candidate weights are suboptimal, the trajectory that comes out, xi, will also be suboptimal, and therefore we add this trajectory to x minus, our pile of suboptimal trajectories. We then iterate this until an optimization fails to find a solution. Okay, so this is our trajectory again, And if we take that data, call it X star, and put it through that big inverse optimal control procedure, the way we sort of look at the progress of this is with iterations are on the x-axis of that iterative loop inside the inverse optimal control. And on the y-axis, we see the estimated step error and hip torque weights, where the gray lines underneath them are the values that were used to generate the step on the left. So we can see that for this simple model, simple cost function, we're converging to the right answer pretty quickly. Okay, so the thing that we want to extend this, or we want to use this procedure here in this work, is we want to deal with models with different levels of complexity. So imagine a 5-link torsoed walker and a 4-link ballistic walker. The goal is to see how well the simpler model can predict the behavior of the more complex one. So just as a proof that these things work, the torsoed walker and the ballistic walker aren't really conceptually that much harder than the compass walker for this framework to deal with. So you can find gates for it. Furthermore, the inverse optimal control procedure works with a little bit, it's a little bit more fussy, it's a little uglier as the dimensionality gets higher, but we get sensible results with a range of different weights. So in the upper right, when you say that then you're penalizing knee torque a lot, or in the lower left where you're penalizing hip torque a lot, the inverse optimal control still works. Okay, so now we have a more complex model, but the question is, what does it mean for a simple model to predict the behavior of a more complex model? So we essentially have to make a decision here about what that even means. So what aspect, for example, of the complex model are we trying to predict with a simple model? And here I've just chosen a metric that I think is, that I kind of care about. So it's a quantity that both models and all walking things probably share, which is a total ground reaction force over the whole trajectory. So the models have different dimensionality, but the ground reaction forces have the same dimensionality and units, and therefore potentially can be usefully compared. That was very carefully worded, to not say too much. Okay, so basically here's what I'm trying to do. We start with a complex model, the torsoed walker, and we assemble all the dynamic constraints, and we also set a speed constraint of 0.6 meters per second. So we're putting it on a treadmill for this task. We then choose some set of weights for the features, and we generate a step X star. So that's what we think of as the observed behavior that we're trying to replicate in some way. We then calculate the ground reaction forces from it, which we're then going to try to mimic with a simpler model. So we do that by setting up the same 0.6 meters per second treadmill constraint for the simple model, but we're searching for the gate which produces ground reaction forces which most closely replicate those of the complex model. So that we then treat this gate, this X star here, as the optimal gate for the simple model, and then everything after here is just the same inverse optimal control procedure as before, although we've secretly refined the cost function inside the weight optimization, which maximizes the gap between the optimal cost and the suboptimal cost, and we found that that just gives nicer convergence properties. Okay, so then what we end up with at the end of that is a weight vector, which it's a weight vector for the simple model's cost function, which when you optimize the model using these weights, you are most closely approximating the ground reaction forces of the complex model. If that's all we did, then I think I would describe this as an extremely complicated data fitting exercise. The real question we need to get at is how generalizable is this simple model using these weights that we've found? So can it predict something about the ground reaction forces, for example, of the complex model in any other conditions? Cool. Okay, so I don't have a great answer to that question, but I can show you some things. So using those weights that we found at 0.6 meters per second, the dashed line is the ground reaction forces of the simple model, and the solid line is ground reaction forces of the complex model, this time optimized at 0.5 meters per second. So we've taken those models and put them on a slightly slower treadmill. And the error between the trajectories are plotted over here on a bigger, blown up by a factor of 3 so you can see them better. And then you can also do this optimization using all those same weights for a range of velocities. It's not a very big range, but you can sort of see how things sort of smoothly change. So we're not really doing a prediction here on the complex ground reaction forces yet, but we can see that if we take the R squared values, where we assume that we are trying to model the complex ground reaction forces as using the simple ground reaction forces. We're finding that we can sort of represent more than 95% of the variability of the complex ground reaction forces using the simple gates. So there might be some regularities we can exploit. The other things we're going to be doing are try and leave one out feature testing, where you can analyze the importance of a particular cost feature by checking how much predictive power it adds when it's included versus when it's not included. We're also interested in trying to compare different models of how well they can predict a single complex one. And of course, we're trying to get back to humans in the end. And I think the model that we want to use for humans will include feet so that we can start including inverse dynamics data. So traditionally, ankles are considered quite important. And one thing that I like about these optimizations is that you can have them do different tasks. So I'd like to do an experiment where you train a model based on two different conditions, say a subject walking on a treadmill with and without some orthosis you're testing, and then use those two different sets of weights. You can make predictions about what a subject might do on different tasks, such as stepping up. And then you can do the experiment and see if that works. Also, all this was written in Julia, so I'll recommend you go to the Julia workshop. It's great stuff. Thanks.
Questions for John?
Other people have to ask questions if you don't want me to ask questions all the time. You have like this. You imagine that you take a model and a gate, and what you see is a reflection of something is being optimized. And you're trying to find out what that thing is being optimized to give the gate. It sounds like you said.
That's kind of an assumption.
And then you have a sequence with lots of parameters or a growing number of parameters to better and better approximate what that objective function might be. But it looked to me like you were doing your costs were like costs on torques or something like that. And the question is, does your set of cost functions span the set of reasonable cost functions, like that include jerk or work or activate muscle activation or something like that? Is there any reason to? I mean, will your things just not be able to catch?
So that's a danger, but that to me I feel is a smaller danger than the opposite. So you can have, you can have a different set of actual features than hypothesized features. And in this case, there's 3 actual features that the person's considering, and we're considering all those 3 plus some junk. So I call them distractors. You're suggesting the opposite case, where the thing that we're trying to approximate is using some features that I'm not including in my hypothesized features.
Right.
I'm more worried about this case, I think, than I am worried about the opposite one, because we can throw in so much. Like we can throw in known redundant, torque dot.
So it's an overfitting problem.
Yeah, so that's why I think the leave one out type of testing is important, because then you can say, if I'm testing torque dot, and torque double dot, what happens to my explanatory power when I take out torque double dot? So it's not going to ever fundamentally say that humans care about torque double dot and not torque dot. But what it's going to say is, if you've got both, if you've got one, then you don't need the other. So you can only get these things down to a certain resolution. But I'm hoping that those things will be predictive enough to be useful.
Any more questions?
During the double support, the mechanical indeterminacy, how is it solved?
Yeah, so that was all bottled up in that. There's one little line in there saying that we set the contact constraints, and so we're basically setting a no double support. So basically, the moment one foot touches the ground with 0 force, the other foot must leave the ground with 0 force. So it's a constraint.
Any more questions?
I was curious what's limiting the speed. So 0.7 is a little slow. So it's because you just can't get really high hip torques, right?
You can get arbitrarily high hip torques. We have no limitation on
step length?
We haven't pushed it. So I've been constraining things to try to make things kind of roughly human-like, but I guess 0.7 0.6 meters per second was really something I just wrote down at one point and haven't. Yeah, I mean, if there's a fundamental limit to what these models can actually do, then we should be able to approach that. Yeah.
Cool. Thanks, John.
We have time for one more. Okay, then thank the speaker.